So in the last class we did orthogonal projection. Okay, let's recall. So suppose V is some vector space. This is some subspace of this. Call it W. Some vector V is given in V, and then we saw that if an orthogonal basis of W is given to you, then you can define a projection of this on W, and this projection will, if this is V, call this say maybe pi WV, okay. And there exists so V minus pi WV would be perpendicular to this plane, to the entire, not the plane, but to the space. Okay. So what we mean is that if you write this as V minus pi WV, then we have V minus pi WV is in the orthogonal space, the space orthogonal to W. Okay. So today we are going to see a generalization of this. Okay. Here we had an inner product space V and a subspace of this with an orthogonal basis, and we said that this is a mid step between, this is actually the induction step of ground splint. We will come back to ground splint, but towards the end of this class. Okay. We begin with a certain generalization of this decomposition of V between W and W perp. So let's recall what we meant by null space and non-degeneracy. Okay. Do you recall what is a null space of a? So you are given a vector space V, with symmetric bilinear form or a Hermitian form. Symmetric bilinear form in case V is a real vector space. If V is a real vector space, so we are taking the vector space V over either reals or complex numbers. Okay. So in particular, when we take it over reals, we take a symmetric bilinear form, and otherwise we take with a symmetric bilinear form or a Hermitian form. This is given. Okay. So this is given, and W is a subspace of V. So do you recall when do we call the form non-degenerate on W? At first, non-degenerate on V. Yes, that's called the null space, right? So yeah, of course, null space is related with non-degeneracy. So null space we defined as null space of V. Null space of the form on V is just V perp. Okay. So now, in particular, null space. If you restrict the form to W, the null space of W, in that case, the form when restricted to W is just W perp. Okay. And then by W being non-degenerate, we just meant that W intersection W perp is equal to 0. Okay. In general, we say, if it is a non-degenerate form on V, so non-degenerate on V this will mean that V intersection V perp is equal to 0. Okay. So that is what we mean by non-degeneracy on V. In particular, if W is a subspace of V, then the form we call the form to be non-degenerate on V. Non-degenerate on W if W intersection W perp is equal to 0. Okay. So the restriction of the form, I mean, if you restrict the form to W, the null space of the form on W is just W perp, and then this just means that there is no vector in W which is orthogonal to all other vectors, okay, except 0. All right. So then this was given as an exercise to you, an easy to prove theorem, that was a form is non-degenerate, a form, say, this is non-degenerate on V if and only if the Gram matrix of the form with respect to any basis is non-singular, right? Okay. And the proof? It was an exercise, right? So, and we gave some hints as also how to proceed to prove this. So the proof begins from observing this definition, null space. Okay. Now, the null the vectors in the null space has a correspondence with the null space of this Gram matrix. How? Almost. It's the null space of the Gram matrix is equal to the coordinate vectors of the coordinates of the vectors in the null space of V. Okay. So the first step, null space of V is equal to, is equal to, at first we are saying that this is if and only if the Gram matrix or the matrix with respect to any basis. So at first we start with the basis, basis B. Before the step 1, suppose B is some basis of V. Okay. We'll write, come back to step 1 in a moment, but let's write it first. B, a basis of V. Okay. Then, and okay, yeah. In tutorial as well. Okay, so in complete proof, great. So you already know how to prove this. Please. Okay, so perhaps we can skip this. Well, the first step at least. Well, both the steps. So step 1, that is the null space is a set of the coordinate vectors of the null space of V is corresponding to the null space of the Gram matrix, whose coordinate vectors are the coordinate vectors of the coordinates of the vectors in this null space. This has been proved. Okay, and the next step, that is it is non-degenerate if and only if it is non-singular. That's also proved, right? Because what it means then, non-degeneracy, x star ay is equal to 0, right? And so in particular, if ay is equal to 0, x star ay is 0, right? And otherwise we have to show that x star ay is 0 for all the x's. That would mean that ay has to be 0. And you get it just by taking the ith element of the standard matrix, or say the ith column of the identity matrix, right? because that would just on the left, I mean in space of x. So what we are saying is that x star ay is 0 for all x. That would mean that this part has to be equal to 0. And how do you show that? Take x to be all zeros except 1 at a single position, say ith position. Okay. And that would give you here the ith component out, and that would be also equal to 0, because this is true for all x's, right? So that would mean that each component of this is 0. That would mean that y is entirely 0. Sorry, ay is entirely 0. Okay. So all right, then you recall the proof very well. So this will just help us in proving the next thing. Okay. Can I work this part? Well, and note one more thing, that is a form is, so no, just have a seat there. Okay. So now, yeah, the thing is, a form can be, do you recall what is a non-degenerate form? Non-degenerate form on a vector space. Just tell me the definition.
There is no vector such that u binary form of u. There is no vector u such that u comma v binary form comma v is equals to 0.
For all of v, and u is not equal to 0. Okay. For equal to 0, this should be 0. But there is no non-zero vector in v such that this is happening for all the vectors. Okay. All the vectors in v. Indeed, that is the definition of a non-degenerate form. And we just wrote that this. Avinash said that this has been done completely in a tutorial. So this was given as an exercise, and then you did in a tutorial. Okay. So now the thing is, I mean, to note that a form can be non-degenerate on the entire space, but can be degenerate on a subspace, right? Why? Because if you take the Gram matrix, a minor of it could be singular, right? And I mean, even if the entire thing is non-singular, some minor of this could be. So, for example, take this Gram matrix, 0, 1, 0, 0. Okay? So, take this minor. This is 0 here, okay? And in particular, it is a singular. But if you look at the entire thing, it is non-singular. Okay? On the other hand, it could also be that some minor is singular, non-singular, but the entire thing is singular. So in particular, that means that a form can be non-degenerate on the entire space, but could be degenerate on a subspace, and also vice versa. That is, a form can be non-degenerate on a subspace, but degenerate on the entire space. Okay. All right, we wanted to write something here, some theorem. Let this be symmetric bilinear form on a real vector space V, or a Hermitian form on a complex vector space V. Okay. Then, well, wait a minute. Let W be a subspace of V. then part 1, V is equal to W direct sum W perp if and only if the form is non-degenerate on W. Okay. That is such a decomposition. I mean, given V, you can write it as some part in W perp W and some part in W perp only if the form is non-degenerate on W. So here, recall we started with an orthogonal basis and we assumed the thing is an inner product, but here it's a more general thing. Okay. And the second thing is that if the form is non-degenerate on V and on W, then it is non-degenerate on W perp. Okay. All right. And of course, we are going to use this theorem here. That is, for we'll translate non-degeneracy to non-singularity of this matrix, of the Gram matrix, with respect to some basis. Okay. Okay, so proof. So this one, let's start with this decomposition and show at first. I mean, that's actually the easy part. Show that this form is non-degenerate on W. Okay. So let V is equal to W direct sum W perp. We are going to show that the form is non-degenerate on W. Okay. Now, what does it mean? Non-degeneracy on W. So we require to show that what? Yes. The intersection is 0, right? But we are writing that V is a direct sum of W and W perp. That in particular implies that the intersection is 0, right? So it is just coming from the definition of direct sums, right? Which is true as, which is true by definition of direct sums. As we require the spaces to be independent. Okay. Or you can write also that which is true as W and W perp are independent, as V is equal to W direct sum W perp. Otherwise, direct sum would not. We should not have called it a direct sum. Okay. So the forward way is done. Okay. Now this one, that if the form is non-degenerate on W, then V has such a decomposition. Okay. So let this be non-degenerate on W. Okay. Let W1 dot 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 WR be a basis of W, and then we extend that to the entire space. Okay. But at first, what is the gram matrix of this form with respect? I mean, what can we say about the gram matrix of this form with respect to this basis? It's non-singular, right? Because we are assuming that this form is non-degenerate on W. Okay. So by the previous theorem, it is non-singular, right? Then the gram matrix G of the form with respect to this basis of W is non-singular. Okay. Is it legible for all of you, or should I write it somewhere else? I'm just writing that the gram matrix of the form is non-singular, okay, because it is given to be non-degenerate on W. Okay. Okay. Now let's extend this basis of W to a basis of the entire space. Okay. Let's extend W1 dot WR to a basis B equal to W1 dot WR, comma, say U1 dot UN minus R of V. Okay. Then the gram matrix of the form with respect to the basis B would be of the form so these three we do not know. We can put some things here and here, but note that on this corner we will have the gram matrix corresponding to W1 to WR, right? Because this one should be just given by Wi Wj. Okay, so that matrix G just sits here. Okay, and here you have some other things. Okay, called B, C, D. Okay, so this is the gram matrix. I mean, I just want to say that there is a gram matrix in of the form in W. So maybe we can denote it by GW. Okay. Okay. And we know that this matrix is invertible. Okay. Actually, GW would make the notation just a bit complicated. Okay, fine. I mean, just to remind us that that is not the full gram matrix, but the gram matrix of, I mean, in that subspace corresponding to this basis. Okay. So maybe we keep this assertion and remove up to this. Okay. we erased everything except the assertions. Okay. Now, what we must show is that W has such a decomposition. Okay. Now, in particular, if this is the case, what can we say about this B and C? Suppose we have a basis with respect to which the gram matrix looks like this. This need not be the basis, but some other basis. Okay. So this is the gram matrix corresponding to W. This dimension won't change. The matrix might change. Okay. If you take a different basis. Similarly, this one would correspond to what? Gram matrix of this. I mean, exactly. Gram matrix with respect to this one is this one. Okay. Now, note that if in some form this B and C are 0, then what we can say that the elements in here are orthogonal to this ones. Okay, because this was just like Wi Uj. Okay, in this ones, as well as this was a symmetric or Hermitian form. So here we will get the corresponding ones. Here. So either Wi Wj or Wi Wj bar. But if it is 0, then it is 0 here as well. Okay. So if we could make this to 0 by some change of basis, then what it will mean? That all the elements here are orthogonal to W, and all the elements here are orthogonal to the space spanned by these vectors, right? So that would give us then a decomposition of V in such a form. Okay, because the basis of this, which are corresponding to W1 to WR, each of the basis elements are orthogonal to this space, and each of the basis elements of this is orthogonal to this space. And moreover, the entire thing is a basis of V. Therefore, you can write any vector in V as a sum of an element of W and an element in the span of this. Okay. So that is definitely going to give us, let us write V in this form, right? So what we have to do now? To find a change of basis which makes B and C both 0. Then we are done. And do you recall how the gram matrix changed by a change of basis? Right. P star, the gram matrix, and then P. Okay. So now let's take that change of basis matrix. Let's consider a change of basis matrix of the form I 0 I and some unknown thing here. So G C D. Okay, this is unknown yet. Okay. But if this is the change of basis matrix, I mean, at first, whether this qualifies as a change of basis matrix, what we require? Invertibility. And look at this matrix. Can you say whether it's invertible or not? Right? Why? It's an upper triangular matrix. Yeah. So its determinant is just a product of the diagonals. Okay. 1. So indeed, we can take this to be our change of basis matrix. Now, we would fix E in such a manner such that, I mean, in the changed form of this and this becomes 0. By the way, if we keep, and here I and these ones are of this dimension. So this is IR and this is I n minus R. Okay. Yes. Well, what how does the identity matrix look like? It's 1 on the diagonals and 0 everywhere else. It's also 1 on the diagonals, right? So this is an problem. Okay. So yeah, all we now require is to fix E such that the changed basis matrix would be 0 here and 0 here. But first, we are trying to note what will happen to GW. after you make this change. Okay, so call this matrix a P, okay, and then where we should write, maybe we clear up the right part. Okay. Yes.
So basically, it's saying that in orthogonal matrix can change the basis.
Of course, because I mean, how do we change it? So when we wrote b dash equal to bp, what we did, this was the new basis, right? This was the old basis. And what were these matrices? These were just the linear combination of the basis elements of the old basis which were expressing the new basis, right? Now you can do the same with the old basis, recall. So you could write that as b dash q equal to b. And then if you take the composition of these, you get this is b dash qp. Okay, this is the basis, and you are representing the basis elements in terms of the basis itself. And we know that every vector has a unique representation with respect to a basis. So in particular, these ones are also given by the columns of the identity matrix, the coordinates with respect to, I mean, the coordinates of the basis vectors with respect to this basis are just the columns of the identity matrix, right? So that would mean that QP is the identity matrix, right? So it comes from the definition of a base change matrix that this is invertible, and for every invertible matrix you will get another basis. All right, let's swipe this part out. So I hope everybody is awake so that we are not going to miss any part of this proof. Okay. So this matrix will be changed by, so if P is the matrix of change of basis, matrix of change of basis, then the new gram matrix, well, the gram matrix with respect to the new basis would be P star. Now what is P star? Let's write it down completely, because I mean the board is, there is not enough space to write 2 lines there. So we go in just, I mean, we write it in one go. Okay. So what will be P star? Can you tell me? Yes. Yes. E should be here, and here will be E star. 0 would be there. I would be just I. Okay. So that would be IR, I n minus R. 0 here, E star here, and here this matrix GW B C D, and here the original P. So IR, I n minus R, 0 and E. Okay. So all we care is to make this one 0, right? This one will be just the bar transpose of this part, right? So please express this corner in terms of these blocks. Okay, just this corner, just this corner after you multiply all this. Okay, yes. The rightmost, right, thank you. Yes. Thank you, Dipta. Yes. So you would just write this, well, at least this corner. Here. Okay, at first the first part, this is an R cross R, this is an R cross R thing, this is an R cross R thing. Well, if you multiply this part, this would be just GW, right? And then this will just give GW on this corner. And you could also see it directly because we are not changing anything on the first part of the basis because this is just the identity matrix on this part. Okay. So this is GW. Okay. Now, what happens here? That's the question. Okay. So after you multiply this, you just get B here, right? And then you multiply this here. So you get GWE plus B, right? GWE, yeah, right. E plus B. And some entry here, some entry here. Actually, this would just be bar transpose of that, but don't bother. We just want to make this 0, okay? To select E in such a manner that this is becoming 0. Okay. In order to make GWE plus B equal to 0, we must choose we may choose E to be equal to minus GW inverse B, and we can write this as an inverse by exactly because on W the form is non-degenerate. So we know that GW is non-singular. And therefore the inverse exists, okay? And therefore we can indeed write, I mean, GW inverse B, the negative of that, this makes sense, okay? So choose E to be of this form, and then you get just 0 there, okay? All right, that would ensure also that this part is 0, okay? And so your Gram matrix after this change of basis with respect to this, I mean, after the change of basis where P is the change of basis matrix, becomes of this form: a block here, 0 here, 0 here, and some block here. Okay. So this finishes the proof because this would be then the Gram matrix corresponding to W bar. Okay. So please let me know if any part of the proof seems subtle or it's not clear. Yes, Parvati.
So the matrix multiplication.
Yes.
These are sub-matrices.
These are blocks. Yes.
Blocks multiply in the same way as the elements.
Yes, of course. So you can actually check this. This is we are using block multiplication here, but you can look term by term. Okay. So what we are doing? These are the first R elements. Okay. These are multiplying with exactly the first R rows. This is a square block. This is a square block as well. Okay. And so now when you multiply this, this is again multiplying with this one. Okay. So what we are doing here, you just verify it with the right dimensions that this indeed works. Okay. So yeah. Now, yeah, that was just the block multiplication of the matrices. Actually, this is an easy exercise, and it should have been done already in the previous course where you learned about matrices. Okay, I mean matrix and matrix multiplications, but nevertheless this is easy to verify. So please check it. Okay. Now, any other thing except that? That is any difficulty with the argument? That is, if this and this are non-zero, why this implies that V is indeed decomposing at W direct sum W part? Is that clear to you? Right. So here, okay, up to this, it's clear by the block multiplication, right? And then we are just putting E to be equal to minus GW inverse B. And we can indeed, I mean, put E equal to this in this one. What happens? This GW times GW inverse, that becomes identity, and you are getting minus B there. You sum it, you get 0 there. Okay. So if GW is invertible, you are allowed to choose in this manner. I mean, you can choose E, whatever E you choose, this matrix is always invertible, right? It's an upper triangular matrix with all ones on the diagonal. Okay. So now you can actually choose E in this form, because I mean all we require is that the Gram matrix on W is invertible. Okay. And this is so because we know that, I mean, this is non-singular if and only if the form is non-degenerate on W, and that's given to you. Okay. So that was one of the that was actually the only hypothesis in the theorem, that the form is non-degenerate on W. Okay. This star? Well, now note that when you change the basis matrix, okay. So at first, what is the definition of a Gram matrix? How do you define a Gram matrix? You are given a basis, say V1 dot 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 Vn, okay. And you define the Gram matrix as, please repeat the definition. Yeah, a bit louder, Adrija. Vi comma Vj, perfect. Yes. Vi Vj. Okay, that is the ijth entry, right? Okay, and that the matrix changes by, I mean, the Gram matrix changes by P star A P that we have seen, so that we have shown earlier, right? So this is the Gram matrix with respect to a given basis V1 to Vn. Okay, now note that if the form is symmetric, we are given the form to be symmetric or Hermitian, right? If the form is symmetric, the gith entry is just the, I mean, Vi Vj is equal to Vj Vi, right? So the matrix is symmetric. We actually did it in the class. That is, the form is symmetric if and only if the matrix is symmetric, and gave it as a homework to you. That is, the form is Hermitian if and only if the matrix is Hermitian. Okay. Now, what it means the matrix to be Hermitian? Vi Vj is equal to Vj Vi bar. So if Vi Vj is equal to 0, Vi Vj is equal to 0, then Vi Vj bar is also 0, right? And that's why, I mean, this, if this one is 0, this one would be just the bar of it, which would also be 0. Okay. Just from the definition of a Gram matrix and from the symmetry or the Hermitian symmetry of the form. Okay. Yes. Any other question? So at least we are getting this to be 0. This is clear to all of you, right? Okay. And then why this is corresponding to the Gram matrix of W parp? Is that part clear to all of you? Sandeep, could you please just wake up? So why is this corresponding to the Gram matrix of W parp? That is a question. Why this? I mean, this is actually. If this is 0, why this is the Gram matrix of W parp? Is this point clear to you? If not, I can explain it again. But if it is not, please let me know. Yes. So let me know from where, from which part you are sleeping. I can explain again. So what are the things that you missed? Well, for the rest of the class, this was, we just completed the proof of this. Now we should go into proving this, okay? But at first, let me see whether he has any doubts. This was the last part. There we defined P, and yeah. So just take your time and let me know whether, we cannot wipe any part because this will remove significantly the portion of the proof. Yeah. Just a bit louder. Instead of Sandeep, you can also ask me. Okay, okay. Then it will be quite difficult. Okay, you have to see the video or read the notes. Okay. Okay. All right. So for the, at least for the rest of you, is it fine? Arnab? Yeah. Please tell me which part then. Okay. Yeah. Sure. So that part is 0. At least this can be made 0. That's clear to you, right? Now, suppose you have. So what we require to show. All right. Let's clear up this part and explain this. Okay. Okay. So suppose B is equal to W1 dot WR and some, well, if we are changing by this matrix, we are not changing the basis, the part W1 to WR, but the rest of the basis elements, okay? So some, instead of U, we must denote it by something else now. Say V, okay? V1 dot V n minus R. Okay. Now this is a matrix with respect to, sorry, this is a basis with respect to which the Gram matrix of the entire space looks like. Let's not denote it by G. This could be confusing even if there is a sub W there. So GW 0 0 and the Gram matrix of the span of this. Give that a name. Okay. So let capital U be the span of V1 dot V n minus R. Okay. And oh, sorry, not the span, but we wanted to give. Okay, yeah. If you name this GU, sorry, U, then you can write here G sub U. So GW and G sub U are the Gram matrices of the span of this and the span of this, right? Now, Arnab, what does this 0 here mean in terms of the basis vectors? What are the elements here? Recall the definition, or you just gave a while ago. This is Vi Vj, right? So these ones are the product of some element from here and some element from here. Exactly. So these, all the basis vectors, the vectors in here and the vectors in here are perpendicular on each other, all of them. Okay. So in particular, you get that this U is in W perp, right? On the other hand, if you have some vector which is perpendicular on W, that would mean that, well, some vector V equal to C1 W1 plus dot 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 plus CR WR plus say D1 V1 plus dot 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 plus Dn minus R Vn minus R. Okay. Now we would like to say that this, I mean, U is inside this. On the other hand, we are taking an arbitrary vector V such that V is in W perp. It suffices to show that this one is going to be 0. Okay. How do you show that? Yeah. Tell me. We just require to show that this, I mean, so if you represent V in this form, then this is just 0 and V is just in the span of V1 to Vn minus R. How should we proceed? It's on not only for Orno, for the entire class. Please let me know. Yes. Yes, Kaushik. Yes. So here we have just shown that there exists a change of basis which makes this 0, right? And that means you have, I mean, keeping this unchanged, you have changed the rest of the basis in such a manner that the gram matrix of, I mean, of this subpart of the span of U is just this one, and the gram matrix of this is this, whereas these vectors are perpendicular on each other. Okay. So since every element in the span of this is perpendicular on the span of this, that means U would be a subspace of W perp, right? Now we are taking an arbitrary element in W perp. That would look like this, right? Some element in V. Well, W perp, we do not yet know that W perp is given by the span of this. Okay. All we know is that U in particular, the span of this is a subpart of, I mean, is belonging to W perp. Now what you are doing, you are taking an arbitrary element V in W perp, V in W perp, and expressing it in terms of this basis. Okay. If you can show that this part is equal to 0, you are done. Yes.
So you can write V minus Vn to one side
Yes.
and take that to the other side.
V minus this,
So
right?
V1 up and
Right. Okay. So call, I mean, give this, maybe give this a name, dV1 to this, maybe call it V prime. Okay. And you want to write it, okay, just a minute. So you have V minus V dash is equal to C1 W1 plus dot 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 plus CR WR. Yes?
this side is in W, but that should be in W.
Yes, right. This is in W.
So that should be in W.
Yes, right. And then? Exactly. Very nice. Okay. So W and W perp are orthogonal on each other, and so that would mean that V minus V prime, this, well, we also know that this V prime is in U, is in this space, right? Because U was defined with the span of this. Okay. It's also in W perp. Okay. So again, V dash by definition is in span of well, we don't need to span or write span of this. It is in U, which is in W parm. Okay, so that implies V minus V dash is also in W parm, right? And in particular in the intersection of this and W, right? And why this is equal to 0? Right, very nice. That implies V is equal to V prime. Okay. Or no? Is it fine? Thank you. Okay. And it's a shame for me, but could you please remind me your name again? Zinedine. Thank you, Zinedine. All right. So we're done with this part. Now the next one, right? This is non-degenerate on V and W, then it is non-degenerate on W part. Okay, what it means? In terms of the matrix again, the gram matrix again. So let G be the gram matrix of W with not W, sorry, V. Okay, at first we take such a basis, okay, W1 to WR and V1 to Vn minus R, Vn minus R. This one a basis of W and this one a basis of W parp. Wait a minute. Can we do this? Yes, of course, because it is given that this is non-degenerate on W in particular. As soon as it is non-degenerate on W, we have such a decomposition. Okay, this is actually called an orthogonal sum decomposition. Let me write it down somewhere. Okay, so you can also make a star or a small box in one part of your copy, and this is just a small definition, but we should do this. So orthogonal sum, if say you have a set of subspaces W1 dot 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 Wk such that Wi and Wj are perpendicular, that means all the elements in Wi are perpendicular to all the elements in Wj for all I and j such that I not equal to j, then okay, sorry, and V is a sum of W1 dot 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 Wk, that is every vector in V can be expressed as a sum of vectors in W1 dot 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 Wk, then in fact we have V is equal to W1 direct sum dot 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 direct sum Wk. Okay, just check that from the definition of direct sums that this is indeed the case, that is these are independent spaces. Okay. Okay, in particular here we are having that V is the orthogonal sum of W and W parp. V, well, W direct sum W parp is also orthogonal sum decomposition. Moreover, in all such cases, we will call this not the space orthogonal to W, but the orthogonal complement of W, because the intersection is 0 in all the cases where W is, I mean, where the form is non-degenerate on W. Yeah.
Even
Yes.
we know that W and W perp are already independent.
Right.
So dimension of W plus W perp is
Yes.
n plus d. Sorry, R plus d.
R plus D.
Right.
Right.
That is a subspace of V. So that can
Yeah.
be at most n. So
Yes.
D can be at most n minus r. Right.
No, actually we extended it. Remember, we extended it to the full basis.
We just need to show that U is equal to W perp. Right.
Right. Yes.
So we already know that U is a subspace of W perp.
Sure. Oh, okay. You are giving another proof.
Yeah.
Okay.
If
This
we just know that we know that D can dimension of W perp can be at most n minus r.
dimension of W perp can be at most n minus r. Right. So if you assume the dimension of U to be less than n minus r, then your argument starts.
We already know that U is a subset of W perp.
Right.
So n minus r should be less than equal to D.
Sure.
And
Yes.
we already know that D can be at most n minus r. So
Sure.
equal to n minus r.
D can be at most. Okay. Wait a minute. So you are saying that D is wait a minute. D is the dimension of W perp. Okay. And then you are taking
W perp plus W perp.
W direct sum W perp.
Dimension will be r plus D since those two are integral.
Yes. So dimension of this would be R plus D. Sure.
That is a subspace of V.
That's a subspace of.
V like W plus W
Yeah,
perp
of
is
course.
subspace. So it
Yeah, unless it is well, W plus W perp is a subspace.
subspace. We don't know whether it's V or not, but it's a subspace of V.
Okay.
Matter.
Oh, but yeah, the intersection is 0. That already is coming from the non-degeneracy, right? So you can always write this in this form. Okay, sure. Yes.
Can be at most n, right? R
Right.
plus D
Of
can
course.
be
Yes.
at
This can be at most n
So D can be at most n minus r.
because this is a subset of V. Yes.
So D can be at most n minus r.
D is less than equal to n minus r. Right.
We again know that U
E is the subspace. Very good. Yes.
yeah,
Yes.
So then we know that D is
D.
greater than n minus r.
Very good. Yes.
D equal to n minus r.
Sure. Sure.
Goes to 60.
Sure. That's also a perfect argument. Thank you. Okay. So then let me write the full thing. So since V is in this, so that means dimension of dimension of U is less than equal to dimension of W perp, and we just saw that this is less than equal to, oh well, dimension of W perp was taken to be D, okay, and dimension of U was n minus r. Okay, so we have the inequality from both sides, and therefore D equal to n minus r. So U is indeed the full space W perp. Very good. Thank you. So both of the proofs are very nice. Thank you, Sneomi and Zinedine. So now we are going to do something. We are going to prove the second part. Okay. So this is non-degenerate. This is non-degenerate on phi and also on W. That would imply that it is non-degenerate on W perp. How do we proceed? We write down the gram matrix of the form W with respect to this basis. Okay, with respect to the basis this. Okay, let's clear up the other things. Okay. And can I wipe this part out as well? Thank you. Sorry. All right. Yeah.
Sir, can you explain once again why V minus V prime belongs to W prime?
V minus V prime. Okay. Where was V prime?
V prime is
V prime was in W perp and V W perp. We also took V to be in the W perp. Okay. So that's why there and V minus V prime should also be in W perp. Okay. So this gram matrix with respect to this basis would now look like what? GW, GU, sorry, not U. Now we can write it GW perp and 0 here, 0 here, right? And we say that it is non-degenerate on W. That would mean that GW is invertible, right? So determinant of GW is not equal to 0. Okay, and we also know that the determinant of the entire thing is not equal to 0 because it is non-degenerate on V, right? So since it is non-degenerate on V, we get that determinant of G is not equal to 0. So if these two information suffices to show that GW perp is not, the determinant of this is not equal to 0, then we are done, right? So what's the relation between the determinant of G and the determinant of GW and GW perp? Any guess? Yes, it's a product, right? So determinant of G is equal to determinant of GW times the determinant of GW perp. How do we prove this? I guess you have not seen the proof earlier, right? Okay. Note that G, which is equal to GW perp, you can also write it as GW 0 0. Replace this one with I, okay, identity. Okay. And here replace this one with I. Okay. Of course, this is I n minus r and this is I r. 0 0 GW perp. All right, you see this, the dimensions matches exactly. I mean this is of dimension r cross r, and this is n minus r. This is also dimension n minus r. So this is perfect, right? And then what do we have? Determinant of G is equal to the determinant of this times the determinant of this. Now what is the determinant of this? Yeah, determinant GW, right? You expand it in this, I mean on the with respect to the last column, then the previous column, and then the previous column, and go on. You just get up to 1 here, and then it is the determinant of GW. Okay, the same happens here as well. Okay, determinant of GW times the determinant of GW perp. Okay. Now if this is not equal to 0, this is not equal to 0, would imply that this is not equal to 0. All right. If this is 0, then the entire thing would be 0, and the form would be degenerate on V. Okay. So determinant of GW perp is not equal to 0. That is, the form is non-degenerate on W perp. Okay. All right. Yes. Non-degenerate just is synonymous to the gram matrix to be non-singular, right? By a theorem that you said you have, I mean, was completely proved in a tutorial, which we left as an exercise earlier. Okay. So, in particular, both of these assertions are done. Okay. So now, given a vector, I mean, in such a case, when the form is non-degenerate on W, you can, since you can write V as a direct sum of this and this, you can always decompose a vector V in terms of something in W and something in W part. Okay, this would be called an orthogonal decomposition of a vector in V. Okay, and the part that lands in W would be called the orthogonal projection of V into W. Okay, so here definition of orthogonal projection in general. Okay, we are not assuming the form to be positive definite here. We are just taking it to be a symmetric or a Hermitian form. Okay, if this if W in V is a subspace such that the form which is symmetric if V is a real vector space and Hermitian if V is a complex vector space. Okay. So if W in V is a subspace such that this is non-degenerate on W, then we have V equal to W direct sum W perp, right, from this theorem. Okay. So let's wipe the theorem now. That is given, okay, so no, what we want to say is that given a V in V, it can be written uniquely as an element in W plus an element in W perp. Okay. Now define pi, say pi W from V to W such that pi W V is in W and V minus pi W V is in W perp. Then we call pi W and pi W the orthogonal projection from V on W perp. Okay. All right. So this is the definition of orthogonal projection in general. And why can we define it in this manner? Because if V has such a decomposition, then the parts of, if you, so that means, let me write down here what it means. For all V in V, there exists a unique W in W and a unique, well, are you using this to denote unique or not? Unique in general? Okay, so unique. Okay, that's great. So W perp in W dash in W perp such that V is equal to W plus W prime. Okay. So this means that there is no other, well, you cannot write V equal to W plus W perp, W dash for some other W1, say from W, and W dash 1 from W perp. Okay. So this decomposition is unique. Now if the decomposition is unique, that would mean that this map which is sending V to this W is also uniquely defined. Okay. And this is just a generalization of the picture that we did earlier for on an inner product space. So we begin the next class from here, and we will go on.